Hey, hello, friends from the Serverless Office Hour. If you're wondering what's happening today and where your usual hosts, I think they're enjoying some very well-deserved time off. In exchange, you get me, but most importantly, today you have the chance to chat with one of the most inspiring leaders in AI and open source today. If you've used Pandas before, you've come in touch with our guest's work. And you may also know him as the CEO of LanceDB, CEO and co-founder of LanceDB. Please welcome to our virtual stage, Chang She. Chang, thank you so much for being here. How's it going, folks?
Hey, it's great to be here. Thank you for having me again, Giuseppe. Great to be on Service Land.
Absolutely. So, Chang, decided to bring you here because, we had a lot of back and forths about serverless technology to power AI applications. And you folks at Lance, you've done a fantastic job in actually building completely serverless vector database. So thank you so much for spending our time with us today. And also, I think congratulations are in order because your team has just raised 30 million in Series A, and there's a comment on me. This is mind blowing.
Thank you. Yeah, appreciate that. It's sort of been our mission at LanceDB to give folks a great option that's easy to use and that gives them a big boost when they're trying to build AI applications or build AI models.
Absolutely. And so before we get into the deeps and like maybe having a look at a little bit of demos, so Chang, if for our audience, can you help me define what a vector database is and why is it useful?
Yes, absolutely. So the way I think about it is with AI, the model is at the core of our interaction with AI, and it's fundamentally changed the world. But what's interesting is that the model's knowledge is capped at training time, right? So if you have private data that you want to get answers from, or if you have more up-to-date data, the model itself is not sufficient. So you need something that can plug in the relevant data from your own sources into the model for it to give you the right answers. And the way that kind of search happens is through this new vector representation or embeddings. And vector databases, it's a new kind of database that specializes in storing this type of representation and serving search workloads rather than sort of what you were used to in previous databases, whether they're like transactional semantics or analytics. But vector databases is more specialized for search.
Yeah, and I guess that if we wanted to pinpoint one of the use cases that we've seen employing vector databases at an increasing rate, I think this would be retrieval augmented generation, or RAG. You folks, you might have heard it from as RAG. And so this is an AI or like context engineering technique whereby you are looking at the kind of questions that the user is asking to an LLM, like the prompt that they are presenting, then perform a step in which we do a similarity search. So we are doing a search within this vector space to find out documents that are relevant from a semantic perspective, bring them into context, and then combine all of this into a context engineer prompt that we're shipping out to the LLM for completion, for inference, so on and so forth. I hope that's clear. But again, if you have any questions, please do let us know in the comment box, and we'll be super happy to take them. And I guess that where I wanted to go today was actually maybe starting by giving you a demo of what retrieval augmented generation looks like, and something that myself, another engineer here at AWS, Kevin Shaffer-Morrison, and LanceDB, actually, we built together, which is a small demo of what a completely serverless retrieval augmented workflow would actually look like. So I'm going to bring up my screen. And this is a code sample that you can download from GitHub, actually. And this is actually how it looks like. So we have here just a this small front end chat app, and this is how it looks like. That is hosted on S3. The usual shebang, S3 CloudFront for like an easy and super cost-effective hosting service. And as you can imagine, this is a single-page application built with React and shipped to S3. But where the magic actually really happens is that we do have two main paths here. One is a path that will allow us to upload document to a document bucket, and this is where we're storing, for example, PDF files. Whenever a document is uploaded here, an event will be sent to our processing queue, and then we will have a Lambda function where LanceDB is actually embedded, and it's running in the same process as the Lambda function. So in this case, LanceDB in this architecture is acting as the vector query and vector creation engine, right? So this is, and what I think is it's genius of the implementation of LanceDB is that LanceDB supports a whole variety of kind of levels of storage. But the one that I fell in love with is actually the native integration with S3. And for this reason, this means that whenever you are ingesting vectors, or like you're searching for vectors, you will only load up the compute that you actually need, and you don't have to have an idle instance just waiting there for queries. I'll just pause there for a second just to understand if there are any questions coming up. And Chang, I don't know if you have any comments on this, but we have been speaking about this for a while, but I never managed to ask you a question about like this kind of implementation and what you think about it.
Totally. Yeah. I mean, I think for the folks who haven't seen this before, I'm a huge fan of using S3 and Lambda. And I think this is really interesting because with RAG and vector search, AI is not the first time where we started using vector search. If you're familiar with traditional machine learning, back when everyone was doing a personalization, recommender engines, we were still using vectors and vector similarity to do the search. I think the big difference is in the workload. In recommender systems land, typically your vectors were smaller. The number of vectors were also a lot fewer. And you had more or less like a constant stream of search queries. And so there was a lot more sort of parity between the amount of compute workload versus the amount of data that you had. And AI kind of changed all of that. So you might have tons and tons of vectors, but the search workloads are actually quite sparse or spiky. And so I think the genius of this architecture is, one, you have all the vectors are stored on S3, so it's extremely scalable. It's durable. You don't have to worry about like losing data from an EC2 or something like that, and it's really cost effective, right? And S3 is what, 20 cents per gigabyte or something like that.
It's 2 cents.
Or 2 cents, yeah. And then on the compute side too, because you have to deal with spiky work traffic and maybe sparse queries, Lambda, I feel, really is the perfect choice because you can always scale to 0 when there's no traffic. And we've achieved this like separation between the compute and storage. And I think especially for individual hackers or startups or like teams starting out, this is really a very, very effective and efficient architecture to build your RAG application or your AI application on AWS.
The other bit that I really love is the fact that you folks, when you started designing Lance, you have taken the idea of a vector space. You've translated the properties of a vector space also on the file system, and this for folks that are not so in love with linear algebra as I am, I'm sorry, I'm a huge nerd, but this means that that essentially your vector space can be sliced up into many small items, and then when you're doing the retrieval, you have this system of indexing that you can use to only retrieve the cells of this vector space that are relevant to your query. So even from a perspective of networking and moving stuff from S3 to the Lambda runtime where Lance is actually running, this means that you're only bringing in the actual data that you need. And again, this is so elegant, and it's actually the reason why we chose Lance to actually architect that. I'll just get you through a quick demo. So
Oh, but sorry to interrupt. Before
yeah.
we do that, I think we have a really great question in the chat
Oh.
from Walber. Yeah, I wrote LanceDB in the AWS console and I couldn't find the LanceDB service. Where is it? I think that's a wonderful question.
Yeah. Hey, Jose, thank you sorry, Wilbur, Jose, thank you so much for that question. Hopefully soon. I don't know. No, I cannot make those kind of promises. But no, actually, there are a few ways that you can consume LanceDB. So the way that we have consumed it for this architecture, it's actually the open source version. So for us it was just say UV add LanceDB, and that's where you get it from, and it's free to use. It's open source, and you can start ingesting and searching for vectors. But Chang, can you tell us a bit more about if you become a bit more serious about doing a vector search, where can we find LanceDB as well?
Yeah, absolutely. So I think to just extend Giuseppe's answer a little bit. So when you're using the open source, that's just an embedded library. So there's no LanceDB service. And this is why the architecture with Lambda works really well here, is that when you're at sort of starting out at smaller scale, you really want to move quickly and you don't have to think about maintaining another service. So this is the perfect choice because there's no service. It's just embedded into that Lambda function. For folks who have bigger data sets, want to maintain indices, so we have LanceDB Cloud and LanceDB Enterprise, where it's actually a distributed service that's running. We manage it for you. So you still have that serverless experience. You don't have to think about servers and clusters and nodes, and all of that is taken care of for you. So there the service can be run in our AWS account or your AWS account.
Yeah, and so I guess the ones that I was looking at, for example, the serverless experience in this case is, for example, you have a nice pricing calculator that will allow you to understand exactly how many vectors you're storing, and like the dimensions of your vectors, how many attributes. So for example, the example I always do is that, I have like 100 million vectors, and I'm going to make a million, or maybe let's go on 10 million vectors. Let's actually read. Let's do more reads than write here. And yes, this is what is going to end up costing you. And I find this extremely more cost effective with respect to the services that I've seen around, especially those that require you to run non-serverless infrastructure. So this is I think really great. And let me just check if there are any other questions. I'm hoping Wilbur, that this answers your question. And just to give you a quick demo of how this works, super quick. We have built this playground that you can download here on GitHub. I'll share a link in a few seconds. But let me just ask a question. So I'm going to ask a question to Claude 3.5 Sonnet about a service in AWS that does not exist. I absolutely dreamed it up. So I'm going to add here, oh, can you tell me what Amazon drone fleet is? I basically dreamed up this service that would be Oh no. Huh. Sorry. My security token expired. There you go. So well, it loads up. There you go. So unfortunately, we didn't have the information for doing this. This is the classic RAG system. Imagine that you have you have a model that has been trained, and Amazon Drone Fleet was introduced a couple of months ago. Sorry, a couple of months after the training. What do we have to do? We need to provide extra context. So let's go here, and we're actually doing it. Let me upload the document that is describing what Amazon Drone Fleet is. So I'm uploading it. It will take just a second to fire up the Lambda to start ingesting this. Absolutely super quick ingestion. What happened is that we put this file onto the SQSQ, the Lambda that was pulling from the SQSQ, picked it up, has done the embedding of it by using Amazon Bedrock. I think in this case, I'm using Titan Embeddings v2. And now this document, if I refresh here, is actually available to my chat. Let me just go and clean up my chat history, and let me ask that question again. And as you can see it, so it's bringing into context the data that I actually need, and it's generating the response. Super easy. If you want to get started with this, I will be sharing a link. But Chang, I know that we've talked about this so many times. There are a few features that we have added since the last time. So for example, you can override all of the system prompts in here, and you can inspect how the actual system prompt works. Or we also had that re-ranking by using some re-ranking models. But I guess my question to you now is, I know that Lance has evolved a lot since last year when we released this sample, and I wanted to ask you more about like the indexing capabilities of Lance now, because for small knowledge bases like this one, it might be okay from a performance perspective to have maybe 100 of documents, but when you go into like the sort of like enterprise needs where you have, I think you guys are managing what billions of vectors right now. So how do you actually make sure that that sort of quantity of vectors, when you're trying to bring it into context, is not going to take a very long time to actually do the retrieval?
Yeah, totally. I think that's a great topic, especially for folks who expect to be managing lots and lots of data. And I think if my experience serves right, um, a lot more people will hit those kind of problems and sooner than they expect to. And I think this is sort of one of the new phenomenons that AI has brought, is that what we've seen is, in the past, before AI, data volume growing by a few times over the course of the year is like considered very large, whereas like with AI, what we see is just like 100x growth in data volume over a year is not that uncommon. And regularly, I talk to folks who are like, "Hey, I'm using whatever tool to manage 50,000 vectors today, and then or like a couple million, but this is like 1% of the things that I want to embed, I want to search through, and so how do I manage all of that data?" And I think this is where you need a vector index, and that search index has a bunch of different parts that we've sort of optimized to give you really great performance even on really large scale data sets. And I would say that, so when we think about search indexing, right? So the core problem is, okay, if you have a table that has 10 million or 100 million vectors, you're not going to want to search through every single one of those vectors to find the 10 that you're looking for. So we need some way to narrow down that search path, that search space. And typically what we see is the indexing for the vectors. There's two buckets of techniques. One is generating a vector index. That can be, that can be tree based, that can be partition based, that can be graph based. And the two most popular techniques for indexing that we see today are, IVF, which is an inverted file index, and then HNSW, which stands for hierarchical navigable small worlds, which is it's a graph index. And I think both have advantages. Many vector databases, most of them should support both, and there's different trade-offs. So the default in LanceDB, especially with the open source, you get is IVF, and the reason for that is IVF. There's a natural way for us to divide the data set into different smaller partitions as part of that index. So then when you do search, you only have to search through maybe like 5% of the data, the really just the relevant partitions. And so what that allows us to do is drastically reduce the amount of memory. And so you don't have to load a giant graph. The other bucket of techniques with indexing and search is compression. So, we have, and typically that's called quantization. So there's like PQ, which is product quantization. There's SQ, which is scalar quantization. There's newer techniques like BQ, which is binary quantization. There's a new one that's coming out, going to be released soon from LanceDB called RabbitQ. And all of these like quantization techniques really is just about compression. So we, instead of storing the full vectors, we store a compressed version of that vector. It's sort of like a lossy compression. And so that becomes a trade-off between sort of the amount of space, memory that's required to store the representation versus the accuracy of the search results. The more you compress the vectors, for the same technique, the more you compress the vectors, the more like distortion you're going to have to get introduced. And so this is actually, so you've added the new features like re-ranking, and so re-ranking is also an important technique in this like index search paradigm, where in order to get to higher accuracy, sometimes we'll add a re-ranking step. Although when it's search, we call it refinement. And so the idea is, if you want to find the top 10, you might do an index search that actually retrieves more than the top 10. That's based on the compressed vectors, but then you retrieve the full vectors just for the set you retrieved, and then you do the full distance computation on that subset. So that means we're getting better accuracy, and you're only doing the full comparison on maybe like 20 or 30 vectors rather than 30 million or something like that. And of course, so this is actually quite interesting, because when we're thinking about more sophisticated RAG and agentic search projects, the indexing becomes and search becomes a lot more complex. So when you start out, you might have just a simple vector search. You might have one column of vectors, but what you will find is you might generate vectors from different parts of the data, different representations of your data, and you might want to have different search methods. So the vector search and semantic search is one way to do search. But if you remember the old techniques and the old search boxes, we always had keyword search and full text search. So that's also something that actually gives good results in certain use cases, right? So we use a lot in RAG, we use a lot of semantic search, but it doesn't mean that semantic search always works better than full text search. So a great example, I think, is, if you search for the term customer, let's say, right? Like if your prompt and your search term had customer in it, full text search is probably going to be better at finding matches and documents that have that exact word, like customer or customers, or custom, or like with roots. But what the semantic search is going to give you is searching results that gives you like user and buyer and early adopter or something like that have meaning semantically similar to customer, but not exactly the same syntactically. And so most of the time, what I see from our community is, as your application becomes more sophisticated, you're going to be combining a bunch of these techniques on a bunch of different parts of your data, and then to get the accurate results that you want. And this is especially true if your data is multimodal, right? Because so it's pretty obvious at this point you could search through text using the vectors, but we can also use multimodal embedding models to use natural language to search through images, and we can process videos, so we can do the same thing, search through videos as well. And so this is an interesting example I wanted to show. So I guess maybe this is something, I don't know if there's voting in the chat or anything like that, but I'm curious how many of you guys have used Midjourney or some similar image generation tool.
Yeah, let us know in the chat box. Maybe just like shout the word that you prefer. So like what were the options, Chang, again?
So Midjourney or sort of any other like open source or closed source image generation tool. I think the project that I'm about to show you is called semantic.art, and we're all familiar, for those of you who've used these types of tools, with that experience, right? There's a chat box, you type in what you want to generate, and we go to the model, and the model shows you the best AI generated art that fits your prompt the best. But we wanted to kind of turn this into a search project in a sort of a tongue-in-cheek way to say, hey, there's actually a huge amount of AI human generated art that we could show you based on your prompt as well. So if we flip over to the screen share here.
Absolutely. Bringing it up.
So what we did was we collected master paintings and artwork from data sets like open access at the Met, and we combined them into we created this application that we called semantic.art. And so this is running on Vercel, and you can search through just a little under 1.8 million pieces of artwork.
Wow.
Via text or images. So let me just show you really quickly. So I've got I've got this little prompt here that we use for testing, right? So we got a little poem, a path on Winzon, and I'm going to search, and it's going to produce sort of the 20 most relevant artworks to my prompt here. So as a path winds on beneath a vibrant sky, sun-warmed grasses whisper secrets low, brush strokes dance with restless energy, quiet fields hold deep intensity. You can read the rest of this, but as you can see from the search results here, these are all fairly relevant to sky and sun-warmed grass and brushstrokes and fields. And so this is but instead of this being generated by the model, this is all human generated art that we actually search through. And so you can see when I hover over one, it shows you the title, not the author, the painter, the artist, and the date and collection and things like that. And you might say, hey, I'm going to explore this a little bit, and maybe I really like this representation, this painting. And so what I can do is then find similar. I can then, instead of searching by natural language, I'm searching by a combination of the image I selected and the prompt, and that way I can kind of modify my search and really explore that space. And so, and of course, when you're thinking about this, it should be fairly obvious that it's going to take more than just that simple vector search, right? Because there's so much that you could potentially express about a piece of artwork, like what is actually being depicted, a set of things. What about the mood and the color palette, and maybe other things like the era and the style, and all of those things um, it can appear in the prompt that a user gives, right? So how do we kind of deal with that? So underlying this for Cell app is basically a LanceDB table. So LanceDB cloud in this instance. So what I want to show you is, first a chart of how we get here and what actually is happening in the background. So the way that we're representing the data is, well, we take Met, WikiArt, and Artsy collections, and we extract a bunch of features from them. We can extract captions, that is maybe a poem or a piece of prose, natural language, sort of more literal depictions, things like keywords that captures the mood, and then of course the image content itself, right? So we can, for the captions that's generated, we generate a text vector embedding for both of those. So we have two embedding columns, and then the image itself also, we generate an image vector. So when you type in a natural language prompt, it can actually search through all three of these vector spaces and then combine using a re-ranking method at the end. And then the keywords themselves become are indexed as a full text search index, so that so that we can parse the prompt for keywords and also make those searches. And of course, those are all sort of combined at the very end. So when we do that search, this is what's happening. This is sort of that when you type in a search query or when you upload an image, the search pipeline behind the scenes is actually quite interesting. So, of course, you'll see that we have, if you have like an image or text, we extract stuff like the mood from the user text. We extract, we create the embeddings for either an image or both the image and the text. And then we do this through a pre-filtered hybrid search. So the hybrid search part is using the full text search and possibly multiple vector searches. And the pre-filter is used to filter on the mood for that particular piece of artwork. And then the very end, we do this re-ranking kind of stuff. This is one of the things that it's really, really interesting because there's so much room for experimentation. You can have tons of fun. You can see where, for your application, where is the biggest bang for your buck when you're creating this kind of search pipeline. So, when we think about this feature engineering pipeline, what happens at the end is you get this kind of table. So I'm in the cloud console now for LanceDB Cloud, and let me just maybe zoom in a little bit just to make the text a little bit bigger. So this is the name of the table, and as you can see, this has 1,700,000 odd rows, and the data looks like roughly what I described, right? So you've got a title, the artist, and then if you click on it, so the image is stored in line. This is another thing that's interesting about LanceDB is even if your data is large blobs like this, you can store this as another column, and we can show the images here. But as I scroll, you can kind of see that. Oh, excuse me. You can kind of see that you have the two caption columns, and then the keyword, and then three different embeddings columns that you can search through. And if you're interested, just want to show you how we generate the captions. So don't pay attention to the file name, but just pay attention to these prompts here. That so we feed it to a VLLM to say, describe an artwork of your choice as a poetic description of the emotion it invokes. Don't make it too long. You can describe it as a poem or prose, right? And so the generated result here, let's just go back, is something like this: mist hangs heavy, a veil drawn across the tranquil lake, the gnarled branches of ancient pines frame. And then the literal one is, if you look at it, right, the natural caption: this photograph captures a serene lakeside scene on a misty day. So it's just describing what's actually being depicted in a more literal sense.
Right? This kind of aligns to the way that humans would describe, but in two different contexts, right? So it's like the poetic is like, okay, if I'm an artist and I want to recreate that sort of mood, this is what the kind of embedding or like the semantic relationship that I want to store. Whereas the description is kind of more, I guess it's appealing to more technical kind of users that are, or like if I'm thinking of like CMSs or like DAMs. So sorry, CMS is like a content management system, and DAM is a digital asset manager or something like that. So it's and are these two the two kind of descriptions that you actually use as a vector to do then semantic search, or am I missing something here?
Right. So we can come back and we can look at the schema for the table. And so so we have these two: poetic caption, natural language caption. These are then embedded as two vectors here, and these are then indexed as IVFPQ, right? And then this third vector column called vector siglip is generated using the siglip open source model being applied on the image column directly to generate the text to image embedding. And again, this is also indexed as IVFPQ. And then we have for the title and the artist, right? We've generated full text search indices so that when we can extract certain keywords out from your prompt, we can use that to run that through the full text search.
Yeah. I just love the comment. The Daimon SR. Interesting to see both poem and natural language for some impressionist arts. I don't know, folks. Have you ever thought that we would have been ending up talking about poetry and impressionist arts on the serverless office hours? I don't know. Let me know in the comment. But yeah, and Chang, thank you so much for I think like gifting us with this moment of poetry and contemplation on on a show that it's actually technical. No, I sorry, I didn't want you to remove the video. Let's sorry. I think we can bring it up. But yeah, folks, in the meantime, while we restore the video, let us know what you think. And like I don't know if you had built something similar and you want to showcase it here, please do let me know in the comment. Let me just bring up the video again. Chang, I think you need to there you go. Okay, so let's resume back where we were. So and Chang, this is the implementation of what we call a modern multimodal data lake, right? So this is where I think Lance has become to his like natural evolution, because back in 2023, 2024, when we were scouting for this sort of technology, we picked Lance because of its integration within the AWS service landscape, namely with S3. That was like the USP for me. But but then it evolved in something that is so much more, and it. I think the seed of that intuition was with the fact that you and your co-founder, you have worked on on data sets that would include a lot of videos, a lot of images. I think your co-founder was working on autonomous driving systems, so that's where the kind of the origin of this is, because for like autonomous driving systems, you need to use a lot of video and a lot of images to build these learning models.
Yeah, absolutely. My co-founder is he's the CTO of LanceDB, and a lot of the designs behind Lance format and LanceDB was inspired by the problems that he solved while working in autonomous driving. And like you're saying, when you're working for these autonomous vehicles companies, you're getting petabytes of data per day off of the vehicles that are sent out for training rigs. And this data includes, time series data that's from the sensors of the car, video data, right, from the cameras, and then LiDAR data, that's 3D point clouds, and then also like manual annotations, right? So you might have somebody who like a annotator who's sitting on the passenger side with like a clipboard and noting like how many times the driver had to take over, and like, well, maybe like some human observations for what was happening at the time. And somehow you had to, like, each training run was, okay, we need to filter that data. We need to clean that up. We need to make sure all of those different modalities of data actually line up with each other, because they're all generated by different sources. And so, how do you align timestamps for like a 3D point cloud and a video versus your time series sensor? And the existing data formats that we had, like Parquet and Iceberg, were not great fit for that. The existing data infrastructure that we had was just not a great fit for that. And so a lot of those problems that we solved gave us the inspiration to say, okay, like, this is an opportunity to create something better that's going to improve the lives of anyone who's working with this type of data.
Yeah, that's beautiful. I just wanted to piggyback on another question coming from the chat, and Demo Kasa, thank you so much for that. How do we have any estimation, or like, can we do like some rough math around how much did it cost to index the whole collection, and maybe the type of embeddings that we're using there? So any comments that you can share on that?
Yeah. So typically the indexing process, you can think of it as a couple of like big steps. So one is the index training. And so what this means is, like, let's take IVFPQ. So the training is, you're going to sample some of your data, and you're going to run a k-means to train to get the central reservoir partitions for the IVF. And then you're going to need to do kind of a similar sort of k-means clustering exercise for the quantization. And then number two is the assignment step, where you're going to take the indexing partitions and the quantization parameters that you've trained, and you're going to apply that to every single row in your table, and then you're going to record all of that, write all of that down. And so this can be done fairly efficiently with LanceDB, because we're pretty good about, okay, not having to hold your whole data set in memory in order to index it. And something like 1.7 million images or vectors, in a reasonable amount of hardware, this should take this would be very quick, like a few, like a 2 to 3 minutes maybe. If you're doing it locally on your MacBook, which you can use a lot more cores, like, this should be it should likely be even faster. And if we're thinking about like actual dollar cost for indexing, if you look at the LanceDB pricing page, there's no separate cost for indexing. This is all kind of included in in the management and the right side cost for LanceDB Cloud. And so this is and I think, as Giuseppe was showing earlier, this is we made the system extremely efficient. So you're only paying for like what you actually use, and you don't have to pay for just lots of instances to hold the vectors even when you're not using it.
Yeah. Folks, I'm also posting a few links to the blog of LanceDB. So there's an article that I found particularly interesting in actually like understanding the IVFQ index. So I'm posting both on Twitch and on YouTube as we speak. But yeah, but that was kind of the thing that I was alluding to when I was saying, this is the way that we are translating these abstract high-level concepts of like a vector space into the actual file system, because that is actually bringing in I would say the advantages from a perspective of network chatting and storage, and even the possibility of like not having to have all of your data set when doing index training, which is I didn't think about that when we were talking about that, and I like just only realizing it now. But that's again yet another amazing amazing consideration.
Thank you. Yeah, the last thing I wanted to show everybody is you can obviously type in natural language to search through multimodal data, but you can also just use the same modality, right? So I can do an image search. I uploaded this image of Napoleon crossing the Alps, and I can basically just upload this image and it'll get embedded, and then we can find similar images, right? So Napoleon crossing the Saint Bernard, different version of this painting, and I wanted to show you this particular search result because this is one of my I'm a big fan of this one. This was from last year, and instead of Napoleon, it's a picture of a monkey. And
can you zoom in a bit?
And then, yeah, so basically maybe the zoom function is broken here. But
folks,
yeah, so
it's live demos.
Yeah, exactly. But so I can find similar images to that, and then of course you can see the Napoleon paintings, but then also like cavalry, right? So it's picking up features like the horse, a sword, maybe like period some military uniforms, and then of course like kind of absurd paintings, right? Like the dog and the horse. So it's very interesting. You can see like what actually gets captured in the embedding and what comes out, right?
Yeah.
And so you can then use this. You can keep going to explore your space. So now, hey, this one is interesting, is actually a samurai battle instead of European battles, and so I can actually then keep exploring this different branch in the search space. So now I'm moving into Asian art here. That's like there's some Japanese art, and maybe this is Armenian, right? And so you can see these a lot that are a lot more similar to the anchor image that I selected. So this is sort of like, if you like art, this is a nonstop rabbit hole that you can keep diving into and waste a lot of your time.
I will not confirm or deny how much time I've spent on this. Sorry. Now there are a lot of interesting search queries that you can definitely do. Please do let us know if you're doing it behind the scenes right now, and if you find something interesting. But we are, I think, getting to the top of the hour, so I don't know if there's any like last comment that you would like to share with the rest of the class, Chang. I find always super inspiring chatting with you about this, and I can my key takeaway from this today for me is that also that the properties of you've implemented a system that respects the properties of these abstract concepts so well that also like in training the index, I didn't really think about that. But I guess that the other thing that we have seen is that we can build completely serverless retrieval augmented generation, or like even like search functions for, I don't know, your chatbot or your agent, or I would say even your website, by making use of Lance. You can fit it on a Lambda, or if you're a little bit lazier, well, like I am most of the time, you can just consume it even off the AWS marketplace. I know you guys have launched fairly recently, and some transactions are going on there. So yeah, if you're interested in consuming Lance in one way or another, there's a whole plethora of ways that you can do. But yeah, if you folks are already using Lance, just let us know in the comment. We'd be super interested to learn more about your use cases. And yeah, I guess that would be about it for today, folks. I had the massive pleasure of hosting a few episodes of the Serverless Office Hours, and I will be hosting another one on the 19th of August. I guess it's in a couple of weeks. We will be chatting with the founding teams at Depot.dev. Depot is a build platform that is loved by thousands and thousands of developers, and it's accelerating your build time by hundreds of times. So we'll be live and we'll show you how to offload the costs and the time of building to a completely serverless architecture as well. And Chang, any other observation before we close the stream?
Yeah, I just want to say thank you everyone for watching the stream, and Giuseppe, thanks for having me on again. I've always enjoyed chatting with you and then watching your other content. So for those of you who are in the audience who don't know, Giuseppe is known as the David Attenborough of serverless land. And so if you haven't watched his other streams, I highly encourage you to do so. It's a lot of fun and really useful content.
Oh yeah, thank you for that. I'll just text. Yeah, we do have another show called AWS Let's Build a Startup on and we are streaming on Tuesdays, but this is going to be like 6 a.m. In PST, 9 a.m. EST, but it's a bit more convenient for us folks on the other side of the pond. So folks, I'll close the stream for now, but thank you so much for sticking by. I've been your host, Giuseppe Battista, Senior Solutions Architect at AWS. This has been the Serverless Office Hours. Thank you so much for your time today, and I'll see you in a couple of weeks. Bye-bye.